Now we are going to cover carboxylic acids and derivatives. This first video is an introduction, and we'll be covering properties, classes of carboxylic acids and derivatives, and nomenclature of carboxylic acids and their derivatives. Carboxylic acids and derivatives are carbonyl compounds that contain a non-metal as a substituent on carbonyl carbon. Here it is indicated by symbol Y. So typical nonmetals could be nitrogen, oxygen, sulfur, or one of the halogen atoms, fluorine, chlorine, bromine, or iodine. Common symbol for halogen is X. We encountered symbols X and Y earlier in this course. Other substituent on the carbonyl carbon is typically a hydrocarbon, indicated here as R, or it could be a hydrogen. So if substituent Y is hydroxyl group, OH, then that together with carbonyl group forms a carboxyl group, and carboxyl groups are functional groups of carboxylic acids. So carboxylic acid contains a carboxyl group. Carboxylic acids and derivatives are sp2 hybridized, so they contain sp2 hybridized carbon and oxygen of the carbonyl group, which means that geometry is trigonal planar. Bond angles are approximately 120 degrees. They are not exactly 120, but they get very close to it, and they vary a little bit from one compound to another. Looking at carbonyl group from the side, we can see presence of carbon-oxygen double bond. Carbon-oxygen sigma bond is shown here as a solid line, and carbon-oxygen pi bond is shown with its two lobes. Lobe above the plane of the molecule is shown in black, and one below the plane in white. Also, on the oxygen atom, we can see that there are two free electron pairs, and those two free electron pairs are in hybrid sp2 orbitals. Now, main classes of carbonyl compounds are carboxylic acids. Of course, carboxylic acids have carboxyl group as their functional group. Acyl halides have chlorine, fluorine, bromine, iodine attached to carbonyl group. The most common are acyl chlorides, and they are shown here. Anhydrides have two carbonyl groups attached to oxygen. Anhydrides are named anhydrides because they are made from two molecules of carboxylic acid and with elimination of molecule of water. We'll cover that later in the course. Esters have alkoxy group attached to carbonyl group, and then we have various amides. An amide could be primary, secondary, or tertiary, depending on degree of substitution. Primary amide has monosubstitute nitrogen, so nitrogen forms only one bond to carbon, and that bond is to carbonyl carbon. Secondary amide forms two bonds to two different carbon atoms. One is to carbonyl group, and the other one is to a hydrocarbon. So secondary amide would have NH group. Primary has NH2. Finally, tertiary amide forms three bonds to carbon. Nitrogen of tertiary amide forms three bonds to carbon, one to carbonyl group, and remaining two bonds to two hydrocarbon carbons. So as you can see, primary, secondary, tertiary amides correspond to primary, secondary, tertiary amines in terms of degree of substitution of nitrogen atom. Finally, there are nitriles. At first glance, nitriles do not appear to be carboxylic acid derivatives. They don't have carbonyl group, but actually they are. They are easily prepared from carboxylic acids and derivatives, and they can be easily converted to carboxylic acids and derivatives, and also properties of the nitrile group are similar to properties of carboxylic acid derivatives. So they are studied together with the rest of the carboxylic acid derivatives. We will cover them later in this chapter. Unlike aldehydes and ketones, carboxylic acids and derivatives are stabilized by resonance. That's because the substituent Y, the non-metal atom, has a free electron pair. This free electron pair is delocalized together with pi electron pair of the carbonyl group, and there are two resonance structures, highlighted here in yellow in general terms. That means that pretty much all of the carboxylic acids and derivatives are stabilized by resonance, with the exception, of course, of nitriles, which have a little bit different functional group. So, typical stabilization is that observed in carboxylic acids, where electron pair from hydroxyl group is delocalized together with pi electron pair, and that results in partial charge separation. So, carbonyl oxygen acquires partial negative charge and hydroxide oxygen partial positive charge. The same type of delocalization, electron delocalization or resonance stabilization is observed in esters. That results in somewhat greater stability and frequently a little bit lower reactivity compared to aldehydes and ketones. These two examples of carboxylic acids and esters are more or less typical examples in terms of electron delocalization. Acyl halides, like acyl chlorides, while also exhibiting electron delocalization, exhibit relatively low degree of stabilization. We already covered reasons for that earlier in the course, and the reasons for low degree of electron delocalization, or in other words, low resonance stabilization, are that there is mismatch in orbital size between those of halogens and a carbon. So chlorine, bromine and iodine have orbitals that are much larger and don't match very well orbitals of carbon. So electron donation is not very efficient. Fluorine orbitals match those of carbon very well, but fluorine is highly electronegative and not very good electron donor. So again, degree of electron delocalization in compounds like this and stabilization is very low. For that reason, these compounds of this type tend to be highly reactive. So acyl halides tend to be highly reactive. On the other hand, orbitals of nitrogen match very well orbitals of carbon, and in addition, nitrogen is compared to other nonmetals very good electron pair donor. For that reason, electron delocalization is very efficient, and amides in general are highly stabilized through electron delocalization or through resonance. And here are two resonance structures shown. So in this case, resonance structure on the right is very important. In fact, in biochemistry, it plays a very important role, and this type of bond, when it occurs in proteins, amide bond, is called peptide bond. The degree of resonance stabilization is so great that we consider that carbon-nitrogen bond is partial double bond, and actually it has been observed that there is restricted rotation about carbon-nitrogen double bond. Another important aspect of carbonyl compounds are intermolecular interactions that are present in them. And as you may recall from Organic 1, we can roughly estimate strength of intermolecular interactions based on boiling points of compounds that are of different classes but similar molecular mass or similar size. So amides have by far the highest boiling points, that means the strongest intermolecular interactions. Intermolecular interactions in general present in amides are very strong hydrogen bonds. And because of the high degree of charge separation as a result of electron delocalization, those hydrogen bonds tend to be very strong. Then second strongest would be carboxylic acids. And that's because carboxylic acids also exhibit very strong hydrogen bonding. Somewhat weaker are nitriles, so their boiling points tend to be a little bit lower, but nitriles have carbon-nitrogen triple bond, and as a result those pi electrons are highly polarized. So nitriles exhibit very strong dipole-dipole interactions. Nitriles are not hydrogen bond donors, so on their own they are not capable of hydrogen bondings. There is no hydrogen bonding between different molecules of nitrile. But there is very strong dipole-dipole interaction, and for that reason they exhibit comparatively high boiling points. Not as high as carboxylic acids of similar size, but much higher compared to other carboxylic acid derivatives. Remaining carboxylic acid derivatives in general are capable only of dipole-dipole interactions, and those dipole-dipole interactions are somewhat weaker compared to those encountered in nitriles. So they have about the same magnitude of boiling points and same magnitude of intermolecular interactions. And those would be esters, acyl chlorides, aldehydes, and ketones. And here are shown here is shown resonance again of amides, and structure on the right shows charge separation, which is responsible for such strong intermolecular interactions. Now there is a very interesting fact about carboxylic acids. In general, they exhibit typical hydrogen bonding between different molecules of carboxylic acid. But when they are present in gas phase or in dilute solution in non-polar solvent, such as carbon tetrachloride, then carboxylic acids tend to associate and form a dimer, as shown here. And these dimers are very interesting in that one carboxylic acid serves as both hydrogen bond donor through its hydroxyl group and hydrogen bond acceptor through its carbonyl group, and pairs up with another carboxylic acid who acts the same way. And so those carboxylic acids then, under such conditions of high dilution in nonpolar solvent or in gas phase, behave as if they are molecules with twice the mass, as if they are dimers. As I said, this is not common behavior, and in ordinary solvents, like protic solvents or in high concentration, they tend to exhibit normal behavior and normal typical hydrogen bonding. For the rest of this chapter, we are going to cover nomenclature of carboxylic acids and derivatives. So first, UPAC or systematic nomenclature of carboxylic acids. To name carboxylic acids according to UPAC nomenclature, first we should identify the longest chain that contains the carboxyl group. And that chain is the parent chain. Then we name the parent chain as an alkane. Next, we drop the final E of the name of the alkane and replace E with suffix oic and word acid. Carbon of the carboxyl group must be, of course, at one end of the chain, and it is assigned number 1. If there are any substituents, then we name and assign numbers to those substituents. And that's it. That should complete the naming. If carboxylic acid is complex carboxylic acid, then we name it by adding suffix carboxylic acid for the acid group. We will see some of those examples later. Here are some examples of nomenclature of simple carboxylic acids. For example, one carbon atom, that would be hydrocarbon methane, so we drop the final E, replace that with oic acid, so that becomes methanoic acid. Ethane becomes ethanoic acid. Propane, propanoic acid, and so on. We have butanoic acid, pentanoic acid. Trivial or common nomenclature uses names that were given to carboxylic acids at the time when they were discovered. And this is nomenclature you have already encountered before at the beginning of the previous chapter on aldehydes and ketones. So simplest carboxylic acid, 1 carbon carboxylic acid, is named formic acid, then 2 carbon acetic, 3 carbons propionic. Particularly pay attention when names, trivial and systematic names, are similar but different. As in this case, systematic name is propanoic, while trivial name is propionic. Make sure that you don't mix them up, that you know which is which one is systematic and which one is trivial. And the same is the case with next two. 4 carbon acid is butyric acid, that would be trivial name. So butanoic versus butyric. Of course, it's easiest to always memorize rules how to name carboxylic acids according to systematic nomenclature from the name of the corresponding alkane, and that way you won't mix up similar names. And 5 carbon acid, valeric acid. And then here we have some examples of more complex acids. This particular acid shown here, highlighted in yellow box, should be called benzene carboxylic acid. It's complex, so we should use carboxylic acid, carboxylic suffix, and then acid as a second word. But name benzoic acid is established name. It is so much in use that that's the only name that is used. So in this case, name benzoic acid has been accepted both as trivial and systematic name and is the only one in use. Here is one typical example how we use that carboxylic acid suffix. So this would be cyclohexane carboxylic acid. And even more complex example where we have cyclohexane ring with carboxyl group as a substituent and another substituent methyl group that is on carbon 2 and trans 2 carboxyl group. So this compound is trans 2-methyl cyclohexane carboxylic acid. If you mastered already nomenclature of aldehydes and ketones, this corresponds to nomenclature of aldehydes and is simply an extension of nomenclature of aldehydes, so it should be easy for you. If not, make sure that you go back and really learn nomenclature of aldehydes. When substituents are present, then according to UPAC nomenclature, we use numbers. So we name and number substituent. So in this case, substituent is methyl group. Of course, acid is pentanoic acid, 5 carbons, and methyl group is on carbon 2. So this is 2-methyl pentanoic acid. According to trivial nomenclature, this would be alpha-methyl valeric acid. Again, trivial nomenclature corresponds to that of aldehydes and ketones, specifically aldehydes. So Greek letters alpha, beta, gamma are letters that refer to carbon atoms related to functional group. So carbon atom next to functional group, in this case carboxyl group, is alpha carbon. Any atom next to alpha carbon is beta carbon. So we can have more than one beta carbon. And then next to beta is gamma, and so on. Make sure that you don't mix up the two nomenclatures. So it would be wrong to call this alpha-methyl pentanoic acid, for example. Trivial nomenclature is a little bit more flexible, so we can call this 2-methyl valeric acid, and that will still be acceptable. Here is another example, and this is 3-bromobutanoic acid, so bromine is on carbon 3, or alpha-bromobutyric acid. Again, as in case of aldehydes, and whenever we use trivial nomenclature and Greek letters, make sure that you remember that alpha corresponds to carbon 2 in the chain, gamma, beta to carbon 3, gamma to carbon 4, and so on. And you may have heard of hydroxy acids. Hydroxy acids used in cosmetics are actually alpha hydroxy acids, which will be their trivial name. So here is an example of a shorter chain hydroxy acid. This will be 2-hydroxy pentanoic acid or alpha-hydroxy valeric acid. Nomenclature of acyl halides is based on the nomenclature of corresponding carboxylic acids. We will examine nomenclature of acyl halides on the example of the most common type of acyl halides, and those would be acyl chlorides. For all of the acyl halides, nomenclature rules are the same both for systematic and trivial nomenclature. The only difference is that starting names of the acids are different. They are systematic starting names for systematic nomenclature and trivial names of acids for trivial nomenclature. We start by identifying the longest chain that contains the acyl chloride group, and that chain is the parent chain. Then we replace ending of the carboxylic acid IC with YL and use word that indicates name of the halogen atom, so fluoride, chloride, bromide, iodide. In this case, chloride. Carbon of the carbonyl group, of course, is assigned number 1, and we name and assign numbers to substituents. Finally, complex acyl halides are named by adding suffix carbonyl halide. And here are some examples. First example is acyl chloride with 2 carbon atoms. So corresponding carboxylic acid with 2 carbon atoms would be ethanoic acid. So we drop IC, replace it with YL, it becomes ethanoyl. Since there is chlorine, ethanoyl chloride. Same rules are followed for trivial nomenclature. According to trivial nomenclature, parent acid would have been acetic acid. So this becomes acetyl chloride. Again, dropping IC, replacing it by L and using word chloride. Here is an example of more complex acyl chloride. So then we use carbonyl suffix. So this is cyclohexane carbonyl chloride. And here is an example of acyl chloride with a substituent. So on carbon 3 we have bromine atom as substituent, and this is 4-carbon acid, so butanoic acid. So when we name it as acyl chloride, it's 3-bromo-butanoyl chloride. According to trivial nomenclature, 4-carbon acid is butyric acid. And of course, if we use alpha, beta, gamma, letters of Greek alphabet to indicate position of substituent, bromine atom is on carbon beta. So this becomes beta-bromo-butyryl chloride. Make sure that you distinguish between benzyl chloride and benzoyl chloride. So benzyl chloride is not an acyl halide. Benzyl chloride is compound that has benzyl group, that's C7H7, with chlorine attached to it. Benzoyl chloride is derivative of benzoic acid. Names are very similar, and even when you look at structures, they are rather similar. But these are completely different compounds, so make sure that you don't mix them up. And here is one more example. This is bromide, so just to show you how to name something other than chloride. So this is an acyl bromide. On carbon 3, we have 2 methyl groups, so this is 3,3-dimethyl pentanoyl bromide. Or if we use trivial nomenclature, 5 carbon atoms, parent acid would have been valeric acid, and carbon 3 corresponds to beta carbon according to Greek alphabet, using letters of Greek alphabet. So this would be beta-beta dimethyl valeryl bromide. Just like the nomenclature of acyl halides, nomenclature of acid anhydrides follows the same set of rules both for trivial and for systematic nomenclature. The only difference, again, are the parent names of the corresponding acids, whether we use trivial or systematic parent names. To name an acid anhydride, we use descriptive nomenclature, and both systematic and trivial nomenclature are descriptive. We name each acid residue that makes up anhydride and then add the word anhydride. There are spaces between the names. If the 2 acid residues are identical, in this case we do not use prefix di. In most of the other cases with other classes of compounds, we do use prefix di. For example, in descriptive naming of ethers or ketones. In this case, prefix di is not used. If 2 acid residues are different, then we list them in alphabetic order. And here are some examples. In this case, we have 2 residues from 2-carbon acid, that means ethanoic acid, so this becomes ethanoic anhydride. Simply, we replace word with acid with word anhydride. Trivial name is acetic acid for 2-carbon acid, so this becomes acetic anhydride. Next anhydride is so-called mixed anhydride. It's composed of 2 different acid residues. Using systematic nomenclature, we have 2 carbon and 1 carbon acid residues, so that would be ethanoic and metanoic acids, so ethanoic, metanoic anhydride. Using trivial nomenclature, this would be acetic formic anhydride. Here is benzoic anhydride, anhydride of benzoic acid. And finally, some anhydrides are anhydrides of dicarboxylic acid. That means that they are generated from one single molecule of carboxylic acid. Since that acid has 2 carboxyl groups, loss of 1 molecule of water from those 2 groups will result in formation of anhydride functionality. And of course, we named that after the corresponding acid. So phthalic acid gives rise to phthalic anhydride. To name esters, we need to name 2 parts of the molecule. We need to name substituent on the oxygen atom, and we need to name carboxylic acid residue. Group attached to the oxygen is named as hydrocarbon. That means, for example, as alkyl group, if it's alkyl group, so it could be methyl, ethyl, isopropyl, tertiary butyl, neopentyl. We could name it as alkenyl group, if that's what it is, like vinyl or allyl, or if it's aromatic, maybe it's phenyl. Then we name each carboxylic acid residue by removing the ending IC of the carboxylic acid and replacing it with ending O8. Finally, we name and number substituents on the acid residue. Here is one example. So substituent on oxygen atom is methyl group, so it's going to be methyl. And carboxylic acid residue has 2 carbon atoms, so that's ethanoic acid. We drop IC, replace it with O8, it becomes ethanoate. So this is methyl ethanoate. Trivial nomenclature, so carboxylic acid according to trivial nomenclature with 2 carbon atoms is acetic acid, so this becomes acetate or methyl acetate. In the next example, substituent on oxygen atom is benzene ring, so phenyl, and 3-carbon carboxylic acid has systematic name of propanoic acid, so this becomes phenyl propanoate. Trivial name of 3-carbon carboxylic acid is propionic acid, so trivial name becomes phenyl propionate. So make sure to distinguish trivial from systematic name as they are very similar. Systematic name is phenyl propanoate and trivial phenyl propionate. Here is another little bit more complex example. So again, substituent on oxygen is methyl. And then we have another methyl group that is substituent on the side chain, on the chain of the carboxylic acid. This is also methyl. But these 2 methyl groups cannot be combined because they're on different parts of the molecule. One methyl group is substituent on oxygen, the other one on carbon chain. So we cannot call this dimethyl. Instead, we have to list it as methyl, and then 3-methyl butanoate because this is derivative of butanoic acid. Next example has ethyl group and residues benzoic acid, so ethyl benzoate. Finally, if ester is complex, then instead of suffix -oate, we use suffix carboxylate. So this is methyl cyclohexane carboxylate. Lactones are cyclic esters. It means that they have ester group as part of a ring. According to UPAC nomenclature, lactones are named based on the nomenclature of the corresponding cyclic ketones. So they're actually named as cyclic ketones with oxygen as a substituent. Oxygen as a substituent is, in this case, is part of the ring or a chain, is named oxa. And then we use number to indicate position in which oxygen atom is. Of course, carbonyl group, carbon of the carbonyl group is carbon 1 of the ring. So for example, 5-membered cyclic ketone is cyclopentanone. Corresponding lactone has oxygen in position 2 relative to carbonyl group. So its name is 2-oxacyclopentanone. So we simply ignore the fact that it's lactone and simply name it as substitute ketone. Trivial nomenclature is descriptive. It names these compounds as lactones. So we use name of the corresponding carboxylic acid, of course trivial name, since this is trivial nomenclature. And we actually don't use name of the acid with number of carbon atoms in the ring, but name of the carboxylic acid with the longest chain. And some of those atoms may be outside the chain, those carbon atoms. You will see an example like that later. In this case, of course, all the carbon atoms are part of the ring, so that really doesn't matter. So for carbon atoms, that means butyric acid. We drop final IC and use suffix O lactone. So this becomes butyrolactone. And now we need to indicate where oxygen atom is attached to. It is attached to gamma carbon of the chain. So this becomes gamma butyrolactone. Next example is a 6-membered ring. So that one is named after cyclohexanone. So which means that systematic nomenclature is 2-oxacyclohexanone. Trivial nomenclature, there are 5 carbons in the longest chain, that's valeric acid, that means it's valorolactone. Oxygen of the ring is attached to atom delta of the chain, so this is delta valorolactone. And here is an example where carbon chain is longer than the ring. In this case, if we look at the entire carbon chain and ignore the ring, we can see that there are 5 carbon atoms in the chain, which means that this compound is derivative of valeric acid. Since this is lactone, it becomes valorolactone. And as valorolactone, we name it by indicating carbon that oxygen is attached to. That's gamma carbon. So this is gamma valorolactone. Note the difference between gamma and delta valorolactones. We just covered these two. A systematic name of this compound would be 3-methyl 2-oxacyclopentanone. Of course, carbonyl carbon is carbon 1, oxygen is carbon 2, and then carbon attached to oxygen is carbon 3. Now we're going to look at nomenclature of amides. To name an amide according to systematic nomenclature, we name group attached to nitrogen and used in print italicized capital letter N instead of a number. That's the same way that we use that symbol in nomenclature of amines. Then we name each acid residue as a hydrocarbon, usually an alkane. To do that, we remove the final E of the name of the alkane and replace it with suffix amide. Then we name and number substituents on the acid residue, and that's the name. For the trivial nomenclature, we use trivial name of the acid residue and replace suffix IC with suffix amide. Here are some examples. Very simple example. 2-carbon primary amide, so 2-carbon, that's ethane. We drop the final E and replace it with amide. This becomes ethane amide. Trivial nomenclature. 2-carbon acid is acetic acid. We drop IC, replace it with amide. It becomes acetamide. Next example is slightly more complex. So 4-carbon chain, that means butane, and that's butane amide. We drop the final E, replace it with amide, butane amide. On carbon 3 there is bromine substituent, so that becomes 3-bromobutane amide. Trivial nomenclature, 4 carbons butyric acid, so that's butyr amide, and carbon 3 corresponds to beta carbon according to trivial nomenclature. So it becomes beta-bromobutyr amide. Next example is a secondary amide. Secondary amide has substituent on nitrogen, and in this case that's cyclohexyl group. So that's named N-cyclohexyl. Carboxylic acid residue again has 4 carbons. So that's butane amide. And on carbon 3 we have methyl group. So name is N-cyclohexyl 3-methyl-butane amide. Then we have example of a tertiary amide. Now we have 2 substituents on nitrogen, so name of each substituent will be preceded by letter N, and they will be listed alphabetically. 2 substituents are ethyl and methyl, so it's N-ethyl and methyl. Carbon chain has 5 carbons, so that's pentane amide, and on carbon 3 there is methyl group, so the name is N-ethyl, N-methyl, 3-methyl-pentane amide. Note that we cannot combine the 2 methyl names, the 2 methyl groups. So we cannot list that as N3 or 3N-dimethyl. That would be wrong. Each methyl has to be listed separately. So it has to be N-methyl, 3-methyl, because they are on different parts of the molecule. And finally, here we have nomenclature of a rather complex amide. It's complex because cyclohexyl group or cyclohexane is attached to amide functionality, not because it's tertiary amide. But because it's tertiary amide, we have to list 2 substituents attached to nitrogen, and since they are identical, we will use prefix di. So this is going to be dimethyl. And we have to use 2 letters N. one for each substituent. So it would be wrong to name this N-dimethyl. So it has to be N-N-dimethyl. And since this is a complex amide, we use suffix carboxamide. So this is N-N-dimethyl cyclohexane carboxamide. Now we are going to look at nomenclature of lactams. Lactams correspond to lactones. Lactams are cyclic amides where amide functional group is part of the ring. And nomenclature corresponds to nomenclature of lactones. If you learn nomenclature of lactones, then this is simply trivial extension of nomenclature of lactones. Just like lactones, they are named after the names of the corresponding cyclic ketones. So 5-membered cyclic ketone is cyclopentanone. And so corresponding lactam has to indicate that there is nitrogen in the ring. We indicate that by word aza. So nitrogen atom in a ring or in a chain is called aza. And then by a number we indicate position in which that atom is. So this would be 2-aza cyclopentanone. As in the case of lactones, trivial nomenclature is descriptive, which means we describe the molecule and use word now lactam as subscript. So we find how many carbons are in the longest chain that contains amide group, and all of the carbons may be part of the ring or some may be outside the ring, so keep that in mind. Usually they are all part of the ring, as in this example. So 4 carbons, and trivial name for 4-carbon acid is butyric acid, so we drop the suffix IC and replace that with suffix O, lactam. So this becomes butyrolactam, and now we have to indicate to which carbon of the 4-carbon chain nitrogen is attached to. It is attached to gamma carbon. So the name of this compound is gamma-butyrolactam. Here is another example. That's 6-membered ring, so that will be cyclohexanone. When we name it according to UPAC nomenclature, that becomes 2-aza cyclohexanone. According to trivial nomenclature, there are 5 carbons in a chain, that's valeric acid, so valeric acid becomes valerolactam. Nitrogen is attached to delta carbon, so this is delta valerolactam. And here is an example of gamma valerolactam. So let's look first at the trivial nomenclature. So again, we have 5 carbons in a chain, valeric acid. So we drop IC, replace it with lactam or O-lactam. So it becomes valerolactam. Nitrogen is attached to gamma carbon, so gamma valerolactam. So know the difference between gamma and delta valerolactams. According to systematic nomenclature, this compound is 3-methyl 2-aza 1-cyclopentanone. Cyclopentanone because there are 5 carbons in a chain. On carbon 1 there is carbonyl group, of course you don't indicate number 1. On carbon 2 there is aza group and H. And finally on carbon 3, or actually it's not carbon 2, it's atom 2 that is aza group. And then carbon 3 there is methyl group, so name is 3-methyl 2-aza cyclopentanone. And finally, to finish this chapter, we are going to examine very briefly nomenclature of nitriles. For nitriles, we have actually systematic nomenclature and 2 different trivial nomenclatures. Systematic nomenclature names nitrile after the name of the corresponding hydrocarbon. So we name the longest chain, including carbon of the nitrile group, as the hydrocarbon, usually alkane, and now we don't drop the final E of the name of the alkane because suffix is nitrile, and since it doesn't start with vowel, we don't have problem of having 2 vowels next to each other, so we don't drop the final E. We simply use the name of the corresponding hydrocarbon and then add suffix nitrile. So very simple nomenclature. For the trivial nomenclature, we have 2 different types. Most commonly used nomenclature names nitrile as acid residue. So we look at how many carbons are there, including the nitrile carbon, and name it as corresponding carboxylic acid using trivial name of that carboxylic acid. So 2 carbons would be acetic acid. We drop suffix IC and replaced with suffix nitrile. So this compound becomes acetonitrile. Third type of nomenclature that is almost never used or very seldom used these days, but was used a lot in the old days, maybe before Second World War, names nitriles as ionic compounds, as cyanides. So it names nitrile group as cyanide, as cyano group, as cyanide, and whatever is attached to nitrile is named as hydrocarbon, as alkyl group. In this case, we have methyl group attached to nitrile or to cyanide, so this becomes methyl cyanide. This is not used anymore because inorganic cyanides are toxic, and to avoid mistaking these compounds for toxic cyanides, nitriles are generally non-toxic, organic nitriles. So to avoid mistaking them with toxic inorganic cyanides, we don't use this nomenclature anymore. Here is another example. So in this case, we have propene as longest chain. So 3-carbon chain is propene and alkene, and so this becomes propene nitrile. And finally, this compound you have to memorize. It's complex nitrile. Complex nitriles are named using suffix carbonitrile. So this compound should be named benzene carbonitrile. But the name benzonitrile has been adopted as both systematic and trivial name because it is in such common use. That's the only name that is used, and so we use that name as both systematic and trivial name. So benzonitrile. And so we have reached the end of this video. In the next video, we are going to examine reactivity mechanisms and some of the reactions of carboxylic acids and derivatives.